A battery just came off a production line in southern China without a single drop of liquid inside it. And it did something Toyota has spent 15 years and $15 billion trying to do first. Engineers took a steel nail and drove it straight through the cell. No fire, no smoke, no explosion. Just a quiet green light on a test bench. The company behind it is called Greater Bay Technology, a startup most people outside the battery world have never heard of, quietly backed by GAC, one of China's largest car makers. This isn't a lab curiosity buried in a research paper somewhere. This is a company that says it's building these cells by the gigawatt-hour before the end of this year. And what happened in that lab in April 2026 may have just put a very expensive question mark over the timeline Toyota has been promising the world for over a decade. Quick thing before we go further. If you're into the actual engineering behind headlines like this, not just the hype, subscribing genuinely helps, because breakdowns like this take a stupid amount of digging to get right. Stick around too, because later on we're going to look at one number in Greater Bay's own announcement that Chinese battery experts themselves are quietly skeptical about. It's not the win it looks like on the surface, and we'll get into exactly why. For now, let's talk about the battery that's been running the entire electric car industry for 30 years, and why it was always going to hit a wall. For almost 3 decades, pretty much every electric vehicle on the road has used some version of the same basic idea. Lithium-ion, built around a liquid electrolyte. Think of that electrolyte as the highway lithium ions travel down, back and forth between the two electrodes, every single time you accelerate or plug in to charge. And liquid is a fantastic highway. It's cheap to make, it's flexible, it conducts ions quickly, and it's the reason your phone, your laptop, and your EV all work the way they do today. It's also the reason a punctured EV battery can turn into a fireball on the evening news. That liquid electrolyte is flammable. When a cell gets punctured, crushed, or overheated, that liquid highway can short-circuit and ignite in seconds. Manufacturers have spent decades engineering around that risk, with cooling systems, casings, and software that manages temperature down to the degree. It works, mostly. But it's a patch on a fundamentally flammable design, not a fix. Toyota saw this problem coming before almost anyone. Back in 2010, while most of the industry was still figuring out how to make lithium-ion batteries cheaper, Toyota was already filing patents on something else entirely, a battery with no liquid at all. A solid-state battery where that dangerous liquid highway gets replaced with a solid material, a ceramic-like layer that can't spill, can't ignite the same way, and, in theory, lets ions move even faster than they do through liquid. Toyota didn't just dabble in this. The company now holds more patents in solid-state battery technology than any other company on Earth. Over $15 billion committed, a public roadmap, a promised range of over 1,200 kilometers, roughly 745 miles, on a single charge, a 10-minute charge time from 10 to 80%, a claimed 15-year battery lifespan. On paper, it's not just a better battery. It's the battery that was supposed to make range anxiety a thing people used to worry about. For a decade, that promise sat comfortably in the future, always 5 years out, always the next breakthrough away. And because Toyota was the name everyone associated with solid state, with the most patents, the deepest pockets, and the longest head start, most of the industry assumed Toyota would be the one to actually cross the finish line first. Toyota even said as much itself. Back in 2023, the company announced it had simplified the manufacturing process for solid-state battery materials enough to mass-produce EVs on this technology within 4 to 5 years. That announcement made headlines everywhere. It was Toyota, in its own words, telling the world the hardest part of the manufacturing problem was basically behind it. Then, this year, a company almost nobody outside China had heard of quietly rolled a working cell off a production line. Here's the part that doesn't make it into most of the marketing slides. Having the best patents in the world doesn't automatically mean you can build the thing at scale, and solid-state batteries have a manufacturing problem that patents alone can't solve. Remember that highway analogy. If liquid electrolyte is a river, easy to pour, easy to shape, flowing wherever it needs to go, then a solid electrolyte is a paved road. And you're not paving a normal road, you're paving one that has to be thinner than a human hair, bonded perfectly flat against two electrode surfaces that physically expand and shrink every single time the battery charges and discharges. Now imagine trying to lay that paved road across a surface that keeps stretching and contracting underneath it, without a single crack, without a single pinhole, across millions of cells, at a cost that doesn't make the finished car unaffordable. That's the actual engineering wall. Not, can we make one perfect solid-state cell in a lab? Toyota, and plenty of others, solved that part years ago. The wall is, can you make that same flawless, hairline-thin solid layer a million times over on a factory floor without a single defect slipping through? One microscopic pinhole in that layer, and the whole cell can short internally. This is why, industry-wide, solid-state batteries have spent the better part of a decade stuck in the same place. Brilliant in the lab, brutal to manufacture. Sulfide-based designs conduct ions beautifully, but tend to be chemically unstable, and in some formulations, release toxic gas if they're damaged. Oxide-based designs are safer but more brittle, prone to cracking under the exact expansion and contraction we just talked about. Polymer designs are easier to manufacture, but conduct ions too slowly at room temperature to be practical. Every major lab on the planet, Toyota included, has been picking a lane and trying to engineer around that lane's specific weakness for years. So, the real race was never just who invents solid-state batteries first. Multiple companies did that years ago, at small scale. The real race is who solves the manufacturing wall, who figures out how to pave that microscopic road at industrial volume without it cracking apart. And that's exactly the problem Greater Bay Technology says it just solved. Greater Bay Technology, or GBT, isn't some overnight startup that appeared out of nowhere. It was founded in 2020, based in Guangzhou, and it's an incubated venture out of GAC Group, meaning it has both genuine research freedom and a direct pipeline into an actual automaker's factories and supply chains. That distinction matters more than it sounds like. GBT isn't just a lab trying to convince a car company to take a chance on its tech someday. GAC is already building the cars that will use it. GBT wasn't a complete unknown before this either. Back in 2024, the company set a world record for the fastest EV charging technology on the planet, taking a battery from 0 to 80% in just 7.5 minutes using a different technology called extreme fast charging. So this is a company that already knew how to push charging speed further than anyone else. The question was whether it could do the same for solid state. In April 2026, GBT announced it had done exactly that. Its first A-sample all-solid-state battery cells rolled off the production line. Quick translation, because this term matters. An A-sample isn't a finished commercial product. It's the first real prototype batch, built to prove that a design actually works outside a controlled lab environment, using something closer to real manufacturing conditions. It's the stage where a lot of promising battery chemistries have historically fallen apart. GBT's didn't. Here's the number that matters most. GBT's cells are rated between 260 and 500 watt-hours per kilogram. Hold that thought. We're coming back to it. For comparison, most of the lithium-ion battery packs powering EVs on the road right now sit somewhere between 150 and 300 watt-hours per kilogram. So at the top end of that range, GBT is claiming close to double the energy density of a typical EV battery today. In plain terms, potentially double the range, or the same range from a battery that weighs half as much. And this is where GBT's approach differs from the rest of the field. Instead of picking one of the usual solid-state chemistries, sulfide, oxide, or polymer, and trying to force it to work at scale, GBT built what it calls a composite electrolyte, an organic-inorganic hybrid. Think of it like a paving material engineered specifically to flex instead of crack. It borrows some flexibility from the organic, polymer-like side of the mix, so it can actually survive that constant expansion and contraction we talked about, while still using the inorganic, ceramic-like side to get the ion conductivity high enough to be useful. It's not a totally new idea in material science, but actually manufacturing it consistently at the thickness and precision solid-state batteries demand is the part nobody else had cracked. And the results are what got the industry's attention. These A-sample cells are completely free of liquid electrolyte. They went through needle penetration testing, where a metal spike is driven straight through the cell. They went through crush testing, where the cell is physically compressed until it deforms. They went through thermal shock testing, rapid extreme temperature changes designed to trigger exactly the kind of failure that causes lithium-ion fires. no fire, no explosion in any of the three. That's not a small deal. That's the specific failure mode that liquid electrolyte batteries have never fully escaped, no matter how good the cooling system around them is. There's also the charging speed. GBT says its cells support stable 2 to 3 C fast charging. Without getting too deep into the jargon, that C number is basically a measure of how fast you can safely pump energy into a battery relative to its total capacity. A higher number means faster charging without degrading the battery. Fast charging has actually been one of the biggest weaknesses of earlier solid-state designs, because that same rigid paved road structure that makes them safe also tends to make ion movement slower and more finicky under high current. GBT says its composite electrolyte gets around that specific trade-off, delivering both safety and speed at the same time, something the industry has been calling close to an impossible trinity: safety, energy density, and speed, all in the same cell. So where does this actually go? GBT isn't just showing off a lab sample and hoping someone eventually buys it. Because of its GAC ownership, its first deployment target is already locked in: GAC's hip-tech electric vehicle brand, formerly known as Hyper. These vehicles are reportedly already being engineered with solid-state integration in mind, which is only possible because the battery maker and the automaker are essentially family. GBT's stated target is gigawatt-hour scale mass production and real in-vehicle deployment before the end of 2026. Compare that to Toyota's own public roadmap. Toyota's first-generation solid-state cells are targeted for small-scale production in 2027 to 2028, initially reserved for flagship Lexus models, with early output measured in the tens of thousands of vehicles at most, not a mass-market rollout. GBT, a company most Western automakers had never heard of 18 months ago, is now claiming it will beat that timeline by roughly 2 years, with a Chinese domestic automaker as its very first customer. That's the headline. That's the part everyone's writing about. But there's a catch buried in GBT's own numbers, one that Chinese battery experts themselves have already started pointing at. Go back to that energy density figure: 260 to 500 watt-hours per kilogram. It's a wide range, and it's worth asking why. The high-end, 500, would genuinely be a breakthrough, roughly double what today's best production EV batteries deliver. But the low-end, 260, isn't actually new. It's already achievable with the most advanced lithium-ion cells that exist in production vehicles right now, no exotic solid electrolyte required. So when a headline says GBT's battery hits up to 500 watt-hours per kilogram, that's technically true, and also potentially describing a cell at the very top of its performance envelope, not necessarily what's rolling off the production line in bulk. Until GBT publishes exactly which cells in that range are actually going into GAC's cars, that gap between 260 and 500 is doing a lot of quiet work in the marketing. Then there's the bigger, more uncomfortable question. An A sample is not a finished product. It's proof that the chemistry works outside a lab. It is not proof that you can build it by the gigawatt hour, at a cost that doesn't make the car unaffordable, with consistent quality across millions of cells. That gap, from A sample to actual mass production, is exactly where solid-state batteries have died before, more than once. Across multiple companies, over the past decade, GBT still has to survive B-sample validation, full manufacturing line installation, supplier qualification, and vehicle-level integration testing, all in the same window it's claiming for mass production. That is an extremely aggressive timeline, even by China's already aggressive EV industry standards. Going from a working prototype to a factory floor churning out gigawatt-hours of identical defect-free cells within roughly 12 months isn't just fast. In an industry where 5 years out has been the standard answer for over a decade, it would be one of the fastest scale-ups this technology has ever seen, by anyone, anywhere. And it's not just Western skeptics raising an eyebrow. Ouyang Mingao, one of China's most respected battery scientists, has publicly predicted that solid-state batteries will capture only around 1% of the market within the next decade, despite everything you're hearing right now. Even Robin Zeng, chairman of CATL, the company that controls roughly 40% of the entire global EV battery market and has stayed conspicuously quiet on its own solid-state program, has offered a far more sober read on the technology's real-world timeline than the headlines suggest. So no, This isn't a settled story where China just flipped a switch and Toyota's 15 years of research became worthless overnight. What actually happened is narrower and arguably more interesting. A comparatively small, GAC-backed startup appears to have cracked the specific manufacturing problem, the composite electrolyte that flexes instead of cracks that has kept solid-state batteries stuck in labs industry-wide for a decade. Whether that translates into gigawatt-hour production by the end of 2026, at real-world numbers closer to the high end of that range than the low end, is genuinely still an open question. But here's why this matters even if GBT's exact timeline slips, which, to be fair, timelines in this industry almost always do. This isn't a two-company race. It's a crowded field, and China currently has more entries in it than anyone else. GAC's own solid-state production line, separate from GBT, is targeting mass production between 2027 and 2030 with over 400 watt-hours per kilogram and over 1,000 kilometers of range. Chery has launched its own ultra-fast 6C charging batteries and is targeting a first solid-state EV application this year, with initial batch production following in 2027. Dongfeng is planning 350 watt-hour mass production by late this year. FAW Group has already installed a semi-solid-state battery, one step below full solid-state, in a production vehicle. SAIC's MG4, running on a similar semi-solid chemistry, has already crossed 100,000 units sold in under 8 months. Proof that Chinese consumers and manufacturers alike aren't waiting around for the perfect full solid-state cell to start shipping the closest thing to it. China's government is moving just as fast on the regulatory side. The country's first official solid-state EV battery standard, defining the terminology and classifications the entire industry will use, is expected to be finalized around July 2026, after a public comment period that wrapped up earlier this year. That's not a small bureaucratic detail. Standardizing terminology and safety classification early is exactly what lets an entire domestic supply chain scale in the same direction at the same time, instead of a dozen companies pulling in different directions with a dozen incompatible definitions of what solid-state even means. Meanwhile, outside China, the race is still very real, just slower and more cautious. Mercedes-Benz drove a modified EQS over 1,200 kilometers on a single charge using solid-state cells supplied by the American company Factorial Energy. Factorial also has partnerships lined up with Hyundai, Kia, and Stellantis. Samsung SDI is targeting 2027 for limited premium vehicle production. Volkswagen's investment, QuantumScape, is aiming for initial qualification samples by late 2026 and vehicle integration by 2028. Toyota, for its part, isn't standing still while this plays out. The company is still pushing forward with a new EV factory planned to start producing models this year, one widely expected to eventually build the vehicles that will carry its solid-state cells. It's also continued filing new manufacturing patents, including ones focused specifically on controlling lamination and pressing methods to keep moisture and contamination out during production, and it's working with outside partners like Sumitomo on more durable cathode materials. In other words, Toyota is still trying to solve the exact same manufacturing wall GBT claims to have already gotten past. It just may not be first to finish doing it. So, this isn't really the story of one Chinese invention single-handedly destroying Toyota's battery race. It's the story of the center of gravity in solid-state battery development quietly shifting east, faster than most Western automakers and most Western consumers seem to have noticed. Toyota still has the deepest patent portfolio on the planet, and arguably the most technically ambitious long-term roadmap of anyone in this race. What it may no longer have, for the first time in over a decade of leading this technology, is the lead on actually getting it into a customer's driveway first. So here's where that leaves things. Toyota spent 15 years and $15 billion building the deepest patent portfolio in solid-state battery history, on a roadmap that still, on paper, outspecs almost everyone else. And a 6-year-old startup backed by a Chinese state-linked automaker may have just quietly solved the one manufacturing problem that's kept the entire industry stuck in the lab and beaten Toyota to a production line by roughly 2 years. If you found this as fascinating as we did digging into it, genuinely helps this channel keep making deep dives like this one, and subscribing means you won't miss the next breakthrough in this race, Because at the pace this industry is moving, there will be a next one within months, not years. So here's the actual question worth sitting with. Does being first to patent a technology still matter if someone else is first to actually put it in a car? Or in an industry moving this fast, is being first to market simply worth more than being first to invent?